Hello, my name is Pete Jenier, and today I'm going to present an introduction to PennDOT's ICE policy. We're also going to look at some demonstrations of tools that are used in ICE analysis. What is intersection control evaluation, or ICE? The purpose of ICE is to consistently consider and screen different combinations of geometry and traffic control when a new intersection is being planned or modifications to an existing intersection are being planned. And the goal of this intersection control evaluation is to better inform, identify, and select alternatives that meet project purpose and needs. ICE really is just about making sure that all options are on the table and given fair consideration without one preconceived control strategy dominating the analysis process and ultimately being selected without others being considered. ICE is a scalable three-stage screening process that will be incorporated into DM1X. The thought behind 3 stages is to enable districts to vary the level of effort involved for a given ICE in proportion to the difficulty of the decision-making associated with it. If only one control strategy is feasible for a given intersection, then a project can end at stage 1, and there's no need to advance to stages 2 and 3. ICE is supported by Federal Highway Administration, and a number of states have ICE policies in place or are actively developing them. ICE is consistent with FHWA's goals of having states consider and evaluate roundabouts and other innovative designs and ultimately implement those strategies when they make sense in the appropriate environments and contexts. ICE is focused on intersections. Over the past 15 years, PennDOT has been implementing roundabouts, but has encountered many challenges with doing this, and roundabouts still comprise a small percentage of the new intersections that are constructed each year. In parallel with this, there is increasing use nationally of alternative intersection forms, such as displaced left turns, restricted crossing U-turns, and median U-turns. ICE provides a framework for considering all of these control strategies in a consistent and reproducible manner from project to project, and ensuring that they are given fair consideration throughout the project development process. To the extent that ICE includes interchanges, it includes the ramp terminal intersections of interchanges. ICE would determine whether a diamond interchange has signals or roundabouts at the ramp terminals. However, ICE would not determine if a given interchange should be a diamond form or a partial cloverleaf form. Here are some images of some of the control strategies that will be included in the ICE process and ICE policy. Here are the 3 steps of ICE. As previously mentioned, it will be determined on a project-by-project basis if stages 2 and stages 3 are needed. Each stage of ICE is completed by filling out a form. These forms are relatively short and enable consistent reporting of results from project to project. There is a spreadsheet tool geared towards stage 2 analysis, but there are no tools specifically associated with stage 1 or stage 3 beyond those used for a normal traffic engineering study. Forms are approved at the district level by the district traffic engineer. Now let's take a look at what happens with each stage of ICE. At stage 1, or preliminary analysis, the focus is on determining if there is more than one alternative that is viable for a given intersection or more than one. If there's only one thing that really makes sense to do, ICE can end at stage 1. Much of the analysis in stage 1 is qualitative, and use of tools is going to vary from project to project depending on how difficult it is to determine the viability of one or more control strategies. Stage 2 of ICE is concept design. This is where more detailed analysis is done to help differentiate between multiple alternatives if stage 1 identifies multiple alternatives as being feasible. Concept drawings are prepared for each alternative, the PennDOT ICE tool is used, and other things that generally influence selection of an intersection control are analyzed. Traffic operations, safety using the PennDOT HSM tool, costs, right-of-way impacts, environmental impacts, input from the public and local government, as well as system effects and multimodal effects. ICE for a given project may end at stage 2, or if more than one alternative is still viable, it may advance to stage 3. ICE Stage 3, or Detailed Design Analysis, is intended for complex projects where decision-making is challenging. There are no new specific evaluation criteria in Stage 3 in comparison to Stage 2, but it is an opportunity to focus on 2 remaining alternatives and revisit analysis or conduct more detailed analysis or receive more detailed input from other project stakeholders. When is ICE required? ICE is required for any project that creates a new intersection, any project that creates a medium or high volume driveway, any project that adds a leg to an existing intersection, any project that adds a through lane or a turning lane at an existing intersection or changes lane configuration, any project that changes control at an intersection, such as adding a traffic signal, any project that is full-depth reconstruction of an existing intersection, or other projects as determined by the district traffic engineer. What resources does PennDOT have available to support ICE? The ICE forms that are completed at the end of each stage, the ICE policy, a relatively short document explaining when ICE is required, the longer ICE procedure document that will appear in Appendix AH of DM1X and explains how to do ICE on a step-by-step basis, as well as ICE case studies that show 5 examples of completed forms for 5 typical projects where ICE would be applied. 2 tools will be available as well. FHWA's CapEx spreadsheet is optional for use in Stage 1 to help screen out many conventional and alternative intersection strategies and see what is viable from a pure traffic engineering perspective, and the PennDOT ICE tool, which is required for Stage 2 analysis. Here's a look at the Stage 1 screening form. The form starts off with inputs for the purpose of the project and the location of the project, as well as basic information such as the lane configuration if it is an existing intersection and the turning movement counts. Stage 1 form continues to have a section for crash history input, as well as an assessment of the viability of a number of control strategies. The assessment is somewhat subjective, and there's a certain amount of faith that the person completing the form is going to give each one of these control strategies a fair assessment. At the bottom of the Stage 1 form is a section for approval by the district traffic engineer. The Stage 2 form is the longest form. It begins with inputs for level of service, VC ratio, and delay values from a traffic engineering program such as Synchro, HCS, or SIDRA. The Stage 2 form continues with inputs for cost and crash prediction from the PennDOT HSM tool, as well as an assessment of the multimodal accommodation. The Stage 2 form continues with inputs for environmental, utility, and right-of-way impact assessment, a summary of public input and public opinion on the different control strategies under consideration, and benefit cost analysis values from the PennDOT HSM tool. Finally, similar to the Stage 1 form, the Stage 2 form ends with an assessment of the viability of the control strategies still under analysis. At the bottom is a field for approval by the district traffic engineer. The Stage 3 form is the shortest form. It is highly customizable and intended for users to be able to adapt it to the needs of a specific project and get at the issues that have prevented a preferred control strategy from being selected in Stage 1 or Stage 2. 5 case studies have been developed. These case studies illustrate typical projects where ICE would be applied and have a full set of completed ICE forms corresponding to the number of stages of ICE for each example. The examples are an HOP for a new roadway serving a new residential development, a skewed two-way stop control intersection with operational and safety issues, an urban signalized intersection operating at LOSF, a rural signalized intersection with capacity issues, and a large urban signalized intersection with capacity and safety issues. The PennDOT Ice tool is used at stage 2 of ICE to bring different performance measures together into a benefit-cost ratio and a net present value analysis. The PennDOT Ice tool is based upon a spreadsheet that was developed through NCHRP Project 3110 several years ago. PennDOT has customized this NCHRP 3110 spreadsheet to be focused at the intersection level and to essentially be hard-coded for analysis of certain types of intersections that are explicitly called out in the ICE policy and on the ICE forms. The spreadsheet is a combination of take-in analysis from other programs and perform analysis itself. Crash prediction is input by a user from the PennDOT HSM tool, and vehicular delay is input by a user from the results of Synchro, VisSim, HCS, SIDRA, or other traffic analysis tools. Construction costs are input from the result of a conventional cost estimate, and information related to maintenance and day-to-day operating costs are embedded. Perhaps most importantly, the tool is designed to be quick and easy to use. It should only take a user several hours and not several days to conduct analysis once things like traffic analysis and cost estimates have been prepared outside of the tool, as they would be for any typical intersection study. Now we're going to come out of Excel and do demonstrations of the two tools. First, we will look at the ICE tool itself, and secondly, we will look at FHWA's CapEx tool. The demonstration of the ICE tool is going to be for a case study of two rural highways intersecting in a small town with minor road stop control. This intersection is congested, it has a high crash history, and the congestion is expected to increase as volumes increase. We're looking now at the PennDOT Intersection Control Evaluation, or ICE tool. Here on the Introduction tab, we have some information on the color scheme of the tool and basic use. Moving on to organizational information, we've already pre-populated the items like the location, the date, and in this case the analysis type is going to be focused on at-grade intersections, but we could change this to be ramp terminal intersections, and that would change what happens on some of the following tabs. There would be interchange-specific inputs. Moving on to alternatives master list, we have an opening year of 2017, a design year of 2037. We have peak hour time periods that start at 7 a.m. and 4 p.m., so we don't need to change that. The default is good. We're on a rural minor arterial, and we need to enter our turning movement counts for the intersection. Everything that happens on this sheet is applicable to any control strategy. It doesn't vary whether you have a signal, a roundabout, a stop sign, an alternative intersection, and the traffic volumes really won't vary for those either. They might get distributed out to other points, but they would fundamentally be the same volumes flowing through the project area. Since this tool is focused on life cycle cost, we really don't care whether a volume is a minor street right turn or a major street left turn or anything like that. We simply want the sum of entering vehicles during the peak period, so we can apply delay costs and average delay values to that to look at what is being experienced by all users. So if I wanted to, I could sum my turning movement counts with a calculator and type the results in down here. However, I'd rather let this tool do this for me, and so I've pre-entered my AM peak hour and PM peak hour volumes in the opening year and in the design year. And if I move back to this tab now, you can see that those volumes are summed for me. Last, I need to pick what I'm going to analyze. Again, I've done that in advance of this webinar to save time. And in this case, I'm going to analyze minor road stop, which is the existing condition, traffic signal, and roundabout, which are the two alternatives. So this is really a classic ICE study where we're looking at a signal versus a roundabout at the site of an existing stop sign. I'm now going to hit this setup worksheet buttons, and that's going to do some calculations in the background related to the three control strategies. And what it's also going to do is develop volume profiles and delay profiles. We'll enter delay information later, but we'll have those profiles developed so that you can take your peak hour conditions and extrapolate that out to every hour of the day. So this tool is not only taking into account the delay in the AM and the PM peak hour when it compares different control strategies. It's looking at delay at 10 a.m., 11 a.m., 3 a.m., all those off-peak times as well, using some default values for the profile of volume and the relationship between volume and delay. It's a very powerful feature of this tool that is not even going to be apparent to the average user because it happens behind the scenes, but it's different than a lot of other life cycle cost analysis tools that only take the peak periods into account. Okay, moving on, it's now time to put in cost information and safety information on the cost parameters tab. Here we have some unit costs for things like the cost of a crash in the state of Pennsylvania, the value of time that someone experiences when they're in congestion. Those defaults can be left alone, and we can move on to entering project-specific design, construction, and right-of-way costs. It will cost nothing to build the stop sign since it already exists. It will cost $450,000 to build the traffic signal, and it will cost $700,000 to build the roundabout, plus $50,000 of right-of-way cost. Over here we have some default operations and maintenance costs. How much does it cost each year to supply power to a traffic signal, to perform maintenance on that signal? And likewise, in the case of a roundabout, how much does it cost to illuminate it or take care of the landscaping at it? These costs are built into the tool. They get automatically applied when you select one of these control strategies. For crash prediction, we have the PennDOT HSM tool, and we've analyzed these intersection types in the PennDOT HSM tool, and we're going to type in the results from that tool. The ICE tool doesn't do crash prediction. It relies upon the existing PennDOT HSM tool to do that crash prediction, and a user simply has to type in the results. For stop signs and traffic signals, results come from a safety performance function. There are no safety performance functions for roundabouts yet. They will be completed by NCHRP later in 2018, but at this point in time, the best we have are crash modification factors. So these numbers in the blue here were computed by the PennDOT HSM tool. They could also be computed by this tool because they're simply proportions of the minor road stop crash prediction in this case. There's not an underlying equation. It's simply a percentage of this value based upon observed changes in the field. But soon we'll be able to actually predict roundabout crashes like we can minor road stop and traffic signal crashes with safety performance functions. Moving on to delay, we did some analysis in Synchro and in HCS, and we have those delay values, which again will be entered into the tool, looking at the outputs of another tool. And again, there was just really no need to recreate traffic analysis software. Those that already exists, everyone already knows how to use that. And this simply takes in the values for that, and the numbers we see here get applied. The numbers we see here are the average delay per vehicle, and we want to look at the total delay for all vehicles. So these numbers are multiplied by the total entering vehicles that you previously entered into this tool, and then they're also extrapolated out to other hours of the day using the demand profiles and the demand delay relationships, and then they're even extrapolated out to other days of the week, months of the year, and years of the project. So everything from opening day to design year completion date, so 20 years worth of days, 24 hours of those days, is all multiplied out with this tool. And with that, we come to the results. And first we see the net present value. So that's summing up all of the costs that users experience, like delay and crashes, as well as the costs that PennDOT has to spend, like maintenance and construction, and the smaller number is better in this case. So here, the roundabout, although it has the highest construction cost, it has far less delay and far fewer crashes, and the reduction in maintenance cost as well compared to these other control strategies. So it has the lowest net present value. The signal is next, and the stop sign is highest. And despite the fact that it cost nothing to build the stop sign, the fact that it's operating poorly and had a lot of crashes, it's not surprising that that ranks last. Since we have an existing condition, and this is not a brand new intersection where there was nothing today, we can also look at benefit cost, and we want to compare that. We've chosen minor road stop off of the menu here, and we're going to compare the signal and the roundabout to the minor road stop. And ultimately what we're most interested in is the benefit cost ratio. There are some intermediate values like the delay benefit cost, the safety benefit cost, and the actual dollar amounts associated with those, but this is really the key measure here, the benefit cost. Converting the minor road stop to a roundabout will have a benefit cost of 53.88. Converting the minor road stop to a traffic signal will have a benefit cost of 57.17. So here, the signal wins out just slightly over the roundabout. And so we actually get, in both cases, clearly this is a desirable intersection to do a project at. We get a lot of benefit by replacing this minor road stop. Whether it is a signal or a roundabout, this tool kind of leads us to both in this case, depending on how we want to look at it. And then last, we have a graph that is comparing the net present value. So that was this top part up here. And that is the PennDOT Ice tool. This is a way to really start to apply some continuity from project to project when making these decisions about intersection control. Our second demonstration will focus on FHWA's CapX tool as a way to screen many different alternative intersection forms from a traffic engineering perspective and assess the overall viability. Seen here is an intersection on a suburban 4-lane divided arterial that is skewed, experiences congestion, and has a high crash history. Here we have FHWA's CapX spreadsheet tool opened up. This will be available for download from the PennDOT Ice website, and it is currently available from the FHWA website as well. This is the introduction page. We also have a page of abbreviations used in the tool. And on the third tab, we get to the inputs. You can see we've already entered in our location and our date and that basic type of information. Next, we're going to enter in the turning movement count volumes. CapX only accommodates volumes from one time period, so if you wanted to analyze both the AM and the PM peak, for example, you would need to use two versions of this file. We're going to continue entering in the lefts, the throughs, and the rights. As we finish this up, we have done about half of the input that is necessary to use CapX simply by putting in the turning movement count here. There are other adjustments that could be made, such as truck percentage, but we can leave those as a default value if we don't have any data provided. Now we need to go out to the tab for each intersection we want to analyze. In this case, we're going to look at a restricted crossing U-turn and a median U-turn, and we're going to use the east-west version of both of these because that signifies that we're talking about a major street that is oriented east-west. You can see here we already have results, and that result uses the default lane configuration, and we need to go in and customize that for our specific case study. One warning about CapEx: the image that you see here does not correspond to the lane configuration being analyzed. This is simply a static image that cannot change in response to any inputs from the user. And we see here volume to capacity ratios for each of the 4 smaller intersections in what was once one single conventional intersection. We have VC ratios of 0.69 and 0.67 at the 2 U-turn crossovers, and 0.88 and 0.91 at the 2 half intersections in the middle here. Looking at the lane configuration now, we have 2 right turn lanes on each of our side streets. We only have right turns from the side street and our cut. We have 2 U-turns and 2 major street lanes at each of the U-turn crossovers. And then at the main intersection, we have double lefts, 2 throughs, and single rights in both directions. And it appears that lane configuration is adequately serving traffic volume. So we really don't need to make any changes. In this case, if we had wanted to, we could have simply overwritten the numbers. We're going to move to the median U-turn now and take a look at how that operates. Here we have 3 intersections, the 2 U-turn crossovers and the center intersection where no left turns are allowed. And here, because of the heavy through volume we have on the side street, we have substantially lower VC ratios than we did on the major street with the restricted crossing U-turn. We can look at the lane configuration here. We basically have 2 throughs and 1 right turn lane all around, as well as double U-turn lanes at the U-turn crossover. So just at a glance, we can see that both a median U-turn and a restricted crossing U-turn are feasible. However, it looks as though a median U-turn is going to perform far better operationally. And that's all it takes to assess traffic feasibility using CapEx. Having seen CapEx and the PennDOT Ice tool, it's important to understand what these tools do and do not tell you. CapEx simply provides feasibility from a traffic operations perspective. The PennDOT Ice tool provides the benefit, cost, and the net present value of each control strategy. The PennDOT Ice tool does not tell you what control strategy is recommended and should be built. The control strategy with the highest benefit-cost ratio or the lowest net present value may be undesirable for other reasons or overall infeasible from a standpoint of right-of-way, total cost, or other issues. These are simply tools to help make decisions that ultimately need to be made comprehensively with a variety of factors, some of which our industry does not have any good way to put dollar amounts on and roll into financial analyses. ICE will be implemented very soon. A strike-off letter is anticipated in late January 2018 that will make the ICE policy immediately effective for PS&E projects that are not scoped. Full implementation is anticipated in the summer of 2018. It will apply to PS&E projects that are not yet scoped, other PennDOT projects, new signals, capacity improvements, safety improvements, and so forth, as well as HOP applications. If you have questions on ICE, please contact Dan Farley in the Bureau of Maintenance and Operations or myself, Pete Jenier at Kittleson & Associates. Thank you for taking time today to learn about the ICE policy and related tools.